Okay, now that we've seen the definition of the complex DFT, I want to give some geometric intuition to go along with this that's super interesting, that'll help you to see all of these periodic signals in a different way. So I'm going to find something called a phasor, which is a complex version of a sinusoid. So let's first again remember the sinusoid. What is that? Can't see it enough times. Y of t is equal to amplitude times cosine of 2 pi f t plus phi. So I'll do the plus phi to be consistent with everyone else. Okay, so a phasor, that is the complex analogy of this. So I'll say y sub p of t, so for phasor, is equal to e raised to I times all of that. Or sorry, a times amplitude times e to the I quantity 2 pi ft plus phi. Okay, so this is what a phasor is defined as. These look pretty similar, but actually because of Euler's formula, I'm bringing over some baggage here. So I still have, I say that this is equal to a cosine, but I also have plus a I times a sine of that. So the phasor actually carries along some extra stuff in the imaginary component, but if we look at the real component, then we can always get it back. So I can always say that yt is equal to the real component of the phasor that's corresponding to it. Okay, but the phasors are very interesting to plot and to understand geometrically. So remember, as I told you in the last module, we plot the real component of an imaginary number on the x-axis, and we can plot the imaginary component of the complex number on the y-axis. So let's plot the trajectory of this phasor on the xy plane as we vary time, as time increases. So let me look at one that has an amplitude of 1, and I'll say a frequency of 2 and no phase. So let's look at that. So what it is actually is it traces a circle, a unit circle in fact. It goes around that circle twice over my interval. Because my sinusoid that I'm actually representing with this is the real component, I can think of it as the shadow that this casts on the x-axis. So this is what my sinusoid is actually doing here. If I do a phase shift, let me start these both at the same time so you can see the contrast. Whoops, I didn't want to give away the cool thing. Okay, hang on. All right. So if I look at these, I can see that they're basically the same, but they're a little bit out of sync. So this one starts at 1 in the real component and 0 in the imaginary component. This one actually starts at root 2 over 2, root 2 over 2. But what you see in this representation is that a phase shift corresponds to a rotation. I'll show you that algebraically in a moment. But that's interesting. That gives us a new way to think about phases. And I kind of hinted at this before. You know, you can think of your signals as living on the circle, and shifting them rotates them. But this is making that more mathematically explicit. By the same token, okay, so let me go to a lower frequency, but I will double the amplitude. And I'll also, just for an example, phase shift by pi over 3. So in this case, what you see is that the amplitude is increased from 1 to 2. That corresponds to an increase in radius in the circle. Okay, and also I'm starting at pi over 3, 60 degrees. So you can see that this is also a rotated version of a circle that would have started at 1, 0 there. Okay, so let's just look at this algebraically really quick. We can do this all using rules of exponents. So if I have a sinusoid, first of all, the amplitude just is in the front of it. So you can see immediately that that's going to scale the radius. But to understand why a phase shift is a rotation, we have to use one of our rules of exponents. So if I look at a phasor, which is a e to the 2 pi ft plus a phase shift, and that's I times all of that. Yeah, so just my phasor to start with. I can actually break this apart because my rule of exponents says that a A base raised to something plus something else is the base raised to something quantity times the base raised to that other thing. So I can actually split this up as, I'll keep the amplitude out there, that's just a scale, but I can split this up as e to the I 2 pi ft plus e to the I phi. So when you look at this, what you see, and actually let me put this, oh I'm sorry, not plus, this is out at front. Okay. So my rules of exponents allow me to do the following. I can take my phase and actually write an imaginary number, which is e to the I times the phase, and that turns into, oops, I forgot my amplitude there. That just turns into a coefficient in front of a pure phasor, one that doesn't have any phase shift. And if I look at this together with the amplitude, what I see is that that is the full complex number, which is a coefficient in front of a pure phasor. So if I go back to my DFT definition, these are all pure phasors. When I do these dot products, I'm getting the complex number, which is the amplitude times this e to the I raised to the phase. So you can express both the amplitude and the phase now as a coefficient in front of a pure phasor. That was something that was a little more difficult to do before. But this makes it very nice. So what we do, we really think of the Fourier transform as these numbers on front of these pure phasors. So multiplying by this number, the A will scale the radius, this e to the I theta will perform a rotation. So that's what the complex number does as a coefficient to this phasor. Now here's where it gets really cool. All right, so you know, phasors of a single frequency they just go around circles at different rates. But you know, as we showed, we're actually decomposing with the DFT into many different phasors. The complex DFT, just like we decomposed into many sines and cosines before. So if I come up with a phasor corresponding to the sum of the cosine of 2 pi t plus 0.5 cosine of 2 pi 2t plus pi over 3, little phase shift in there. Here's what I get. So you can think the first phasor is this arrow, and I actually put the other phasor at the tip of that arrow, and they actually trace something out together, which is a little more complicated than just going around a circle. And if I look at the projection, if I plot the projection on the real axis like this, then this is the shape that it makes. Okay. But even just looking at this, you start to get these beautiful shapes. Now here's what it gets really cool. So if I go back and make a square wave by summing a bunch of sines together, so a sine is a cosine shifted by pi over 2, so cosine of that plus pi over 2. And I take every other harmonic and I scale the harmonics by 2k plus 1. Yeah, okay, so if I go in the harmonic series, watch what I get. So this is a square wave represented as a phasor. So all these phasors added onto each other. And so you can see it kind of hovers there, and then it goes back, and then it goes back again, and then it goes back. It's not perfect, but it does kind of stick around here, and then goes back there, and then goes back again. So when I look at the projection, I get this. So that's a square wave. All right, so anyway, these phasors are pretty cool. We're going to talk about in class how to do the inverse of this. So how to go back from all of these coefficients here, a set of them for each frequency, how to go back from that to the time domain. Okay. So thank you for your attention. I hope you thought this was as cool as I did.